Okay, it's setting up. Okay, let me start with a brief introduction about our today's invited speaker, Dr. Weishi Huang. Dr. Weishi Huang is currently a full professor in School of Aerospace Engineering at Tsinghua University, China. His research focuses on numerical study of turbulent flows on the complex boundaries. Professor Huang is also interested in computational biofluid mechanics. He has been developing computational methods for fluid flexible body interactions with the goal of simulating and obtain physical insights into problems from biomechanics. So Professor Huang received Excellent Young Scientist of NSF for China in 2013. He is now the associate editor of AIP Advance and Journal of Mechanical Science and Technology, and proceeding of the Institution of Mechanical Engineer, Part C. He is also in the editorial board of the International Journal of Heat and Fluid Flows, Journal of Hydrodynamics, and the Theoretical and Applied Mechanics letters. So Dr. Huang today will introduce his recent work on vortex dynamics and the lift thrust generation mechanics of flying and swimming. And Dr. Huang, please start your seminar.
Okay, thanks. Let me share my screen. So can you see the full screen of my?
Yeah,
okay,
that's good.
Yeah. Thanks for the invitation of Professor Li and the introduction. So it's my pleasure to give a talk of our recent research about the flying and the swimming. So this is mainly done by one PhD student, Junduo Zhang, and postdoctor, Dong Zhang. So first, I will give a brief introduction to the background and also a brief introduction to the numerical method. And then I will introduce 3 examples, including the Mosquito Flight, the Tuna Swimming, and the Batoid fish swimming. And finally, the summary and the future plan. Okay, so most of us are very familiar with the various kind of biological flying and swimming in nature. Oh, sorry, wait a moment. Okay. Okay, so, and they have excellent performances, and people pay attention to such phenomena for a long time. The one evidence is can be seen from the paintings, like this is made by Da Vinci, and also the Chinese ancient painting. But the understanding of the underlying mechanism is not easy, especially the relation between the flying and the swimming with the vortices, the key part of the fluid flow. And also, study on such problems is also helpful to the development of UUV, MAV, and other unmanned equipment. So it's important to utilize such a mechanism to break through the limitation for traditional propulsion. And until the last several decades, people found the close relation between the flying, swimming, and the vortex dynamics. Okay, so it's disclosed that the superior locomotion ability of flying and swimming in nature is closely related to the vortex dynamics, and the various mechanisms were disclosed, like the leading edge vortex, the trailing edge vortex, and also the vortex interaction in more complicated conditions. I will have a brief introduction to the different mechanisms. Okay, so the leading edge vortex mechanism was first observed in the mechanical model of Morse in 1990s. So it was found to enhance the lift force. But theoretically, so for the 2D case, the leading edge vortex cannot be stably attached. It will increase and then shedding from the wing. So later on, so people found that the LEV can be stably attached by the 3D span-wise flow, and also the centrifugal and the Coriolis force due to the rotational motion. The LEV mechanism is probably the most widely used mechanism for enhancing the lift force. It not only exists in the small insects, but also in other animals like the bird wing, and also the passively falling, rigid rotating wing. And also recently, it was found observed in the swimming fish around the caudal fin of swimming fish. Another one is the tip vortex. So it's prevalent in the fixed wing aircraft, but recently, so it was found in natural flying and swimming animals. The tip vortex is also beneficial for the lift and thrust generation. So in this figure, it shows that the tip vortex together with the leading edge vortex and the trailing edge vortex to form a closed ring structure, like the single ring for the conus ring and the dragonfly, and the more complex rings for the cicada and the sunfish. In more complex situations, the vortex interaction was observed, like the bird block fish school, and also for the animals with complex shapes, like the dragonfly, which have 2 pairs of wings, and the fish with dorsal fin and the caudal fin. They will utilize the vortex interaction passively or actively to improve the flying and the swimming performance. Another issue is the Reynolds number effect. So in nature, so the swimming and flying have a wider Reynolds number range from order of 1 to 9 to 10 to 9. So it have both the laminar region and the turbulent region. So far, the most experimental study done at a higher Reynolds numbers, but the numerical simulation usually is conducted at a lower Reynolds number. So it's also necessary to carry out the simulations at a higher Reynolds number to compare with the experiment, and then we will have more detailed data to analysis and to see the low Reynolds number simulation is how much is similar or how much different with the high Reynolds number case. So for the about several issues, recently we published a review paper in Acta Mechanica. So, and in this review paper, we also introduced some typical physical models for some typical cases. If you are interested, please find it on the journal website. Okay, to do the study, so we first need to develop the numerical method, because such problems usually are also challenging for the numerical method. And here I adopt the immersed boundary method. The basic idea of the immersed boundary method is to add the momentum forcing in the governing equation. And the key issue is how to formulate the momentum forcing to approximate the no-slip condition along the immersed boundary. So, one efficient way is to using the penalty method. So the momentum forcing is formulated by assuming that the fluid particle and the fluid particle and the solid particle are linked by a stiff spring. So in this way, in this method, it's easy to compute the force, but it has the free constant, which should be very large. So it will have some limitation on the CFL number. So recently we have some further development, which is called the projection method. So this basic idea is to consider the momentum forcing in a similar way with the pressure, or both of them are considered as a Lagrange multiplier. One is to enforce the divergence-free condition, and the momentum forcing is used to enforce the no-slip condition. Then they can be solved implicitly. But in this way, so it's inefficient to solve this two parts together, because the pressure Poisson equation should be modified, and the efficient originally well-developed solver is not available. So here we develop improved version. It's called efficient two-step approximation. So we just decompose the momentum forcing and the pressure in step by step, and then we only need to add a small modification to the original solver. And first we solve the intermediate velocity, and then solve the momentum forcing to enforce the no-slip condition, and then to solve the pressure Poisson equation and to enforce the divergence-free condition. So in this way, so the numerical solver has only need to be slightly changed to include the immersed boundary part, and it has a high efficiency as compared with the implicit solving the pressure and the momentum forcing together. So this one has previously much reduced cost to compute the momentum forcing and the Poisson and the pressure. So this one was published in Computers and the Fluids. And then we consider the fluid structure interaction. So this is the fluid part, and we also combine the structure solver. In the structure solver, we can also consider the constraint, like the inextensibility condition, and to efficiently solve this big system. So we also develop a multi-step decomposition. First, we decompose the pressure, decouple the pressure from the system. The constraint the no sleep constraint from the system, and then decouple the structure solver, and then to decouple the pressure from the system. So this can also be efficiently solved in this way. And the temporal accuracy is maintained at the second order. And here is some example. This is the filament flapping and the comparison with previous studies. And also we test at the more complex three-dimensional flapping flag. Okay, so we can also see the complex vortex shading from the flag. So for different Reynolds numbers, so we can see the flow becomes more complicated as the Reynolds number increases. Okay, so another issue is the high Reynolds number, because in nature, so we can often see the flow is at a high Reynolds number, and it's in the turbulent region. And also it has complex and moving boundaries. So because for the immersed boundary method, we cannot have a very refined structure near the boundary, because in the body conformal mesh, the normal direction has a much more refined mesh than the stringwise direction. But in the immersed boundary method, the mesh sizes are similar in different directions. So we cannot have a very much refined mesh in the normal direction. So in this way, we just solve the near wall in the near wall region. We solve the wall model equation. It's called thin boundary layer equation to get the accurate shear stress, and then we can modify the subgrid viscosity, subgrid scale viscosity near the boundary to enforce the wall model. And in this way, we can combine the immersed boundary and the wall model LES to solve the complex moving boundary, high Reynolds number turbulent flows. So this work was also previously published in Physics Flow and the International Journal of Heat and Fluid Flow. And we tested this IB and the wall model LES in solving the high turbulent flow over the sphere. So this is a Reynolds number of 10,000 and 100,000. We can see the flow becomes complicated turbulence. And the comparison of the pressure coefficient along the surface, we can see we can obtain a satisfactory results by using the current hybrid method. Okay, so in the following, I will introduce the flying and swimming examples. The first one is the Mosquito Flight. So in 2017, so the Nature paper was published on about the Mosquito Flight. So it shows that there are several special features of the Mosquito Flight. So it has a slender wing, so with a large aspect ratio. And also it has a high flapping frequency and a small flapping amplitude. The buzzing, so we sound is generated by this high frequency flapping. So in this paper, so it shows that due to the high flapping frequency, so it has a significant rotational drag induced by the high frequency flapping. So this is a significant difference with other insect flight. So then we want to quantitatively study the flying mechanism of the mosquito. we want to see the flow, the quantitatively the flow field and its relation with the lift force. So this is the geometric model. So and then we get the flapping angle, the 3 Euler angle by fitting the experimental data, and also there is a very small deformation of the wing. This is also observed by the experiment. Then we establish the computational model. Okay, so this is the flow field, the vertical structures in a flapping period. So during a flapping period, so we can see 3 lift peaks. So this is the red line is the total lift force. Okay, so and at the these 3 moments, the T1, T2, and T3, so we can see the vertical structures are different. At the T1, the trailing edge vortex is obvious. And at T2, the leading edge vortex is more significant. And at T3, so it's due to the rotation and upward motion. So we can see both the leading edge and the trailing edge vortex. Okay, so and then we want to quantitatively analyze the contribution of such vertical structures to the lift force. So here we adopt the DMT theory, the derivative momentum transformation theory. So the basic idea is so this formulation was derived by these 2 papers. So we can divide the flow region into different sub-regions. In each sub-region, we can calculate this formulation to get the force of this sub-region. And then because this we divide the flow region into R1, R2, R3, because R1 corresponds to the trailing edge vortex, and R2 it corresponds to the leading edge vortex, and R3 also trailing edge vortex, but at a later time. So then we can compute quantitatively the contribution of each part to the force on the body. And now we can see the results for the R1 region. So here the dashed line is the total lift force, and the solid line is the contribution from the R1 region. So it's clear to see that due to the trailing edge vortex, the first peak in the total force is from the contribution of the trailing edge vortex here. And at a later time, when it's shedding from the wing, at this moment, so it has a little contribution to the total lift. So now we can see the first peak of the lift force is from the trailing edge vortex at an early time. And for the R2 region, so we can see the third peak on the total lift is mainly from the leading edge vortex in the R2 region. Okay, and similarly, so in the R3 region, so the trailing edge vortex at the later time contribute most to the second peak. Okay, so this is so in this way we can see more clearly the contribution of the different vortices to the lift generation. So this is a typical example of the flying mechanism. Okay, so from the point of view of the vortex dynamics. Then I'd like to introduce the second example. This is tuna swimming. So for the tuna, so it's not only a delicious dish, but also a very good swimmer. So it has a superior swimming ability. So it has a cruising speed of 6 to 10 full lengths per second, and the burst speed of 20 to 27 full lengths of speed. It also has a long distance migration, so the ability of long distance migration across ocean. For this swimming ability, so it has several good features. One is streamlined body, and also the suniform swimming mode, and also the crescent caudal fin. And also it has some other specialized structures. One is the caudal keel. So, and the other is the dorsal fin, and also the finlets. So we'd like to study more in detail how these kind of structures help or affect the hydrodynamic performance of the tuna swimming. So first we look at the dorsal fin. So we'd like to see how it interacts with the caudal fin, because the vortex shedding from the dorsal fin will encounter the dorsal fin directly. So it's so here we only consider simplified model, tendon 3D flapping fins like this. Okay, so the results are also interesting. So we can see the dorsal fin itself has no difference between the model with the caudal fin or not, but the thrust force on the caudal fin can be increased by the existence of the dorsal fin. So we can see that with dorsal fin and without dorsal fin, the thrust force can be enhanced. The reason is due to the vortex interaction between the caudal fin and the dorsal fin. So we can see in more detail. So the vortex shedding from the dorsal fin can interact with the leading edge of the caudal fin. So as compared with the dorsal fin alone without caudal fin, we can see the much difference. So we say this kind of interaction is called the constructive mode, because the two vortex have the same direction and they will merge and become a stronger vortex. So to see more quantitatively, so the circulation of the leading edge vortex of the caudal fin so will become higher than that without the dorsal fin when the vortex from the dorsal fin meet the leading edge of the caudal fin. And then so at the peak of the lift force, so this one is much higher than that one. So this is evidence for the constructive mode of the vortex interaction. And we also concern the sensitive of this kind of interaction to the parameters, like the distance and the phase difference. So it's also interesting to see that this kind of constructive interaction is insensitive to the phase difference. So for the different phase difference of the caudal fin, dorsal fin, and the caudal fin, so the thrust force and the circulation always higher. And the leading edge of the caudal fin, the different cases, it's a similar position because for the different phase difference, So the flow field will also adjust itself to cause to induce the beneficial interaction. So it's kind of interesting result. So this kind of interaction is found to be robust if the distance is not too small. So that vortex interaction will have some kind of feedback or some kind of adjust by themselves to result in the beneficial interaction. Okay, so then we look at the finlets on the dorsal. So there are 9 finlets on the tuna. So this is according to the observation of the live tuna. During one period, so this is a flapping angles of different finlet. So then we just also fit the angle variation, but from this figure there is some kind of asymmetry. So because it's from the real the real tuna, so we have some kind of data fitting from the real observation, and then we also made some kind of some adjustment to make the flapping symmetric about the center line. So this is our fitting curve. This is the original curve, and then so we have the 9 finlets. So this is the model. So to compare with the real one. So the last one was missed in their observation due to some kind of technical limitation. And so here we also add this one by some kind of extrapolation. So then we have this kind of the complete flapping model of the finlets. Then we can obtain the flow field. Okay, so we can see the very complicated vortex interactions. There are the leading edge vortex, trailing edge vortex, and the tip vortex, and also there's also root vortex. So for comparison, we also simulate the cases without the first 2 finlets, and also without the last 2 finlets, to see the effect of the finlet. It's interesting to see that for the 9 finlet, so it has a lower drag than the 7 finlet cases. Even it has 2 more finlets, because with these 2 more finlets, so it have some kind of effect on the leading edge of the third one. For this one, so the third one, the vortex is much stronger. So but here it's weaker. So then we can see in nature it has 9, and then this looks like a optimal arrangement. And we also check the interaction between the finlet and the caudal and the dorsal fin. So it's seen that at the height of the finlet, so it will more complex interaction, but at the position higher than the finlet, so this interaction is quite similar with the case without the finlet. So for the dorsal fin and the caudal fin interaction, so we may consider this one separately. So and it has it's not much affected by the existence of the finlets. Okay, so we can also consider the caudal keel. So this one was rarely noticed by by the fluid mechanics people or by but the caudal keel was found to be exist in the faster swimming fish. Like the tuna is one typical example. So here we consider this kind of simplified model, but we add the body the body shape, but the body motion together with the caudal keel together to do the simulation. And look at the force. So with and without the caudal keel, the body force are very similar. So this means that the caudal keel has no effect on the body force on the body itself, and the caudal keel itself has the drag force and the power coefficient. So but this one are small as compared with that on the caudal fin. For the caudal fin, it's interesting to see that the thrust force and the power coefficient are higher, become higher than that without the caudal keel. So to see the reason, so we can see that with the caudal keel, so there are a pair of vortices, and this may induce a low pressure region here, as compared with that without the caudal keel. So this will help to reduce the transverse force. And then we check the pressure on the caudal keel. So with the on the caudal fin. So with the keel, so the pressure is higher on the pressure side than that without the keel. The reason is that the stringwise vortex power pair is weaker on the caudal fin compared with that without the caudal keel. So why this pair of vortices are weaker than the case without caudal keel? So we can see the here the 3D vertical structures. So here it has a pair of vortices generated by the peduncle. And then so with the caudal keel, it generates a pair of vortices which are opposite to this one. Then okay, so they together will be weakened as compared with the case without the caudal keel. So this is the reason why the vortices are weaker here, and the pressure is higher by the existence of the caudal keel. Okay, so this is the second example of tuna swimming, and the third example is the batoid swimming. So in nature, there are different species of batoid swimming. So so one parameter is flapping the wave number. So this is a kind of a special motion, so different with the other the tuna swimming. So it like a bird, but when the wave number is small, so it's just like flapping wing. It's called oscillation mode. But when the wave number, the chordal-wise wave number is large, so it's undulation mode. So this one, so it's propelled by the moving traveling wave. Okay, so here we build a model from the real sectional data, and also the span-wise deformation is represented by the amplitude, and the chord-wise deformation can be represented by the wave number. And here I show some results. We can see that the vertical structures are more significant for the small wave number, and the flow becomes more quiet, okay, for the large wave number. So this is 0.8 this case. Okay, and from the thrust, we can see the optimal one is the middle one. So the wave number too large or too small. So they are not good for the propulsion. So then we can see it also has some kind of optimal wave number. And we similar with the mosquito force, we also analyze the contribution of specific vortices to the forces by using the DMT theory. And then the R1 region represents the leading edge vortex, and R3 represent the tip vortex, and R2 the trailing edge vortex. So it's not very exact, but roughly represent each different vertical structures. So this is the results. So from this figure, we can see for the lift force, the main contribution is from the R1 region, the leading edge vortex. But in the swimming problem, we mainly concern the propulsion force, the thrust force, not the lift force. It's surprising to see that the propulsion force is mainly from the tip vortex at R3 region, but the R1 region has the negative contribution. So this is the opposite to our traditional knowledge on the effect of the leading edge vortex. To see the reason, so we check the swimming at different Stokes number. So it's found that the difference is caused by the high Stokes number. So at a low Stokes number, the leading edge vortex has the positive contribution to the thrust force, but the tip vortex has the negative contribution to the thrust force. But when the Stokes number increases, to 0.6 to 1.3, so the tip vortex has a much higher contribution to the thrust force, but the leading edge vortex becomes a negative contributor. So the reason can be seen from the instantaneous field. At a low Stokes number, we can see the main structure is the leading edge vortex. But as the Stokes number increases, so it transformed to the span-wise vortex in the tip region. So this explains why at a high Stokes number, so it has a much higher contribution to the thrust force. And then we consider the flow at a high Reynolds number. So we can see here we compare three Reynolds numbers. The highest one is about the 150,000. So we can see the vortex structures becomes more complicated, and the turbulent state is obvious at the highest Reynolds number. Okay. And as the Reynolds number increases, okay, the variation of the thrust force and the pressure and the power coefficient, the trend are very similar, but the thrust force is increased as the Reynolds number increases, and the power coefficient is also increased as the Reynolds number increases. Okay, the pressure force is increased, but the surface friction, the frictional force on the surface is reduced at a higher Reynolds number. So we can see the vertical structures and the surface pressure coefficient. As the Reynolds number increases, so leading edge vortex becomes stronger, and the lower pressure is lower, and the fluctuation at the rear part becomes more significant. Okay, so And then this is the pressure on the surface. So we can see it's stronger than the lower Reynolds number case, but the fluctuation is more significant. But the high friction region is much reduced at the higher Reynolds number case. And then we see in more detail of the vertical structures. So for at the lower Reynolds number, so we can see the span-wise, this here actually the chord-wise vertical structures. This is from the leading edge. Okay. So, but at a higher Reynolds number, so this leading edge vortex is becomes destabilized, and then after shedding from the body, it becomes more complicated vertical structures. And we can see in more detail. So at a different time during a flapping period, so we can see the stabilization process of the span-wise vortices. So it will have the become one leading edge vortex become multiple helping vertical structures, and then a forest of helping vertical structures. So this is quite similar with the war turbulence, the transition process of the war turbulence, and probably observed for the first time on swimming the fish, the body surface of a swimming fish. And so here we just plot a schematic of such destabilization process. So the leading edge vortex and then becomes destabilized, and then so it becomes a array of the helping vertical structures. So, okay, so that's the main contents I'd like to introduce today. And as a summary, so I just like to give a brief several words on what we've done. So we for the three examples, okay, so the Mosquito Flight, the Tuna Swimming, and the Cod Swimming, we can see that the significant effect of the vertical structures to the lift enhancement and the thrust enhancement. And also at higher Reynolds numbers, we can see the turbulent state, especially the leading edge vortex to helping vortices transformation process. And and we now we may answer partly the question that how much the low Reynolds number study can replace the high Reynolds number study. We can say that when we constant the fluctuation quantity like the noise, so we have to do the high Reynolds number case. In some situations, the variation of the trend of the low Reynolds number case are similar with the high Reynolds number case. And nowadays, the physical model becomes more and more realistic, and I think as a future research hotspot. So in the near future, so the problems include the FSI, high Reynolds number, effect, water dynamics, and flow control are probably the interests of people. Okay, so as also in the near future, I also may conduct some further research on several from several aspects. One is more comprehensive model, like this figure shows that we may consider a complete model like a tuna fish with the specialized structures, and this may be helpful for the design of underwater vehicles. So how the specialized structures can improve the performance. And also we may consider the complex flow condition. So in most simulations, people only consider the very simple inflow condition. So, but to represent the more complicated conditions, we can consider the common vortex street inflow condition, and also the turbulence inflow condition. And also, we have paid much effort to do the multi-phase simulation. So now we developed the numerical method to see the three-phase interaction. So we can consider the problems of the cross-media problems, like the jumping of dorsal fin out of water, and also the diving of a bird into water, like these kind of problems are also challenging to the simulation, and also the underlying mechanisms are complicated. Okay, so that's my talk, and I have several publications, one review paper, and there's several one for the 3 examples. So okay, so that's my talk, and your thanks for the listening, and welcome for question and comments.
Yes, thank you, Professor Huang, for the very interesting talk. So any question from our audience, you can unmute yourself and ask Dr. Huang directly. So I will start with maybe start with my question. Is
Okay.
My first question is when you introduce the implicit inverse boundary method, you introduce you need to reconstruct the same boundary layer to capture the correct the shear stress or viscosity in the model. So because if you consider the boundary layer, it's depend on the Reynolds number. So I'm not sure you generate some reconstruction grid points to capture the same layer. Does this depend on the Reynolds number?
Okay, it's a good question. So here we solve the thin boundary layer equation on this kind of wall layer region. So, but this wall layer region is only refined along the normal direction. So it's like a one-dimensional equation. So in this equation, so we have the eddy viscosity. So in this eddy viscosity, we can solve the high Reynolds number cases. So we can obtain the correct shear force on the boundary by solving this equation. So it is a well developed approach. So you are right. It depends on the Reynolds number. You know, this one X class. So this one depends on the Reynolds number. So it need a kind of iteration process. So for the because first we don't know the X. This one depends on the shear here. So but at first we don't know this one. So we can have some kind of guess and then iterate, and finally we obtain the correct the wall shear stress. So this is a need a kind of iteration. by solving in this region. But because it's only one-dimensional, so the computation cost is not high. Some other simpler approach is like called the equivalent equilibrium model. So just using the log law to estimate the shear force here. But this one is a more generalized approach. Yeah.
Okay, then the vortex generation from the wall to the LES model were determined by this model, right?
So this is called kind of hybrid one. So along very close to the surface, we don't resolve the fine structures. We want to capture the correct shear stress, but because at a very high Reynolds number, this is a very thin layer. So if we want to resolve, maybe 99% mesh need to be used here. So, but at higher region, so it's solved by LES. It's a fine resolved. So like here. So in this region, it's resolved by the LES. So this called the kind of hybrid, very close to the wall. So we use a wall model, but higher, so it's a fine resolved. So we can get the fine structures, flow vertical structures in the flow field.
Okay.
Yeah. So this one, so we have two publications on this, and this may previously, so people consider the discrete forcing immersed boundary method. So this one are the early try of by using the diffused forcing immersed boundary method with the wall model LES, and so it's quite convenient or easily used for this kind of moving boundary problem, moving boundary high Reynolds number problem.
Okay.
Yeah. Thanks.
So any other question from our audience? So if not, maybe I can use the time to ask my questions. So my second question is about the Mosquito, the flap pattern.
Yeah.
So I know now many research group and company that are trying to generate some small flying insect.
Okay.
So they are trying to mimic the flapping and pattern of the mosquito or other animal. So I'm wondering, because now we can do all the simulation, get the details, and we can understand why the flapping pattern looks like that. But for artificial insect, we have much better choice to have the material property. For example, the better flexibility of the wing. I'm not sure if we should follow the same flap pattern, the same frequency as mosquito, or we can get better flying insect by using select some better materials can support the fly.
It's a good question, because I only do the simulation and no experience to the real manufacture. My understanding is that now it's still very challenging to do the man-made equipment close to the real one. So the performance of the man-made now is still lower than the real one, because one key issue is when the machine becomes small, so no enough. One is a material problem. Another one is the power. So no enough power. The engine cannot be made small enough to provide the enough power to support the flight. Probably swimming it's okay, but for the flying problem, so it should be light enough, and then to provide the sufficient lift, so it should also be flapping strongly enough. But nowadays, I think it's still not available to like a Mosquito or other small one. So we see the Festo company made a big one, Jackfly, but it's quite big, and the flapping amplitude is much higher than the real one. So if if one want to make a kind of aircraft very close to the real one, so I think now it's still a big challenge, and yeah, it's even for the swimming, underwater swimming, the efficiency is also lower than the real one. So now it's still challenging to make a swimming robot fish with a similar efficiency with the real one. So I think that's a challenging issue. If we see a robotic fish swimming, if we cannot distinguish it's real or man-made, then it means that it has high efficiency, as high as the real one. But now,
so do you think this is because the robot fish have rigid body, but the real fish have a flexible body?
That's
a better control of the vortex.
That's probably one issue, but generally I think that's still challenging to flying or swimming like real one. There are many factors. I think even it's soft, it's deformable, but there are many other issues. Yeah. So anyway, so I think this is a big challenge so far, and to perform better, so people like use the like a fixed wing or like the blade, like the blade, right? A blade propulsion, but that one can have the faster speed, so the natural propulsion has its advantages. So I think it's still necessary to further develop the natural propulsion. Yeah.
Yeah. So talk about the swimming efficiency. Actually, the fish swimming, the flexible fish, it's not like the propeller. Propeller is another kind of way to swim. Talk about the swim energy efficiency. It's much higher than the fish, right?
So there are, I think there are different definitions of the propulsion efficiency. Yeah, so I don't know exactly yeah, so it have some kind of higher performance, like the speed or like the power, because that one has a much higher power input. for the propeller. So, but it's quite different different style. Yeah. But for the natural the propulsion, so I think the efficiency, I don't know exactly how to compare these two forms. Yeah, but for the propeller, obviously, so it has a high noise, and yeah, for I don't know, for the high speed one, so it will have other issues like cavitation or other issues. Yeah.
Yes, there's a lot of open question and challenge in this field. Yes, thank you very much, Professor Huang. So then, if we don't have more questions, then we'll end here.
Yeah. Okay. So thank you. If you have more questions,